All right, on to 4.2. This, my friends, is one of my favorite theorems. Well, I don't know. I think it may be one of my favorite theorems in math in general, but I just think it's really fun to apply. It's definitely one of my favorite facts in precalculus, that's for sure. So in this section, we're going to be talking about the rational zeros theorem. And just to give you a little bit of motivation, the idea is this. We're interested in finding the zeros of polynomials. Okay, we want to be able to solve polynomial equations. Sometimes there are polynomials that can't be factored by the standard techniques like what we reviewed in section 2.2, right? In those situations, if a zero is given to us, then we can just use the methods from the previous section, right? 4.1 to reduce the polynomial. But that's usually not the case, right? It's like usually we would just be confronted with a polynomial and not know really anything about it. So if none of the zeros are known to us and the polynomial can't be factored using standard techniques, well, what in the world do we do? Well, that's where the rational zeros theorem comes into play. So the rational zeros theorem tells us that if you have some polynomial, okay, with integer coefficients, so the coefficients on your polynomials are all integers, and of course the first and last term are non-zero, right? So if this is the case, then c, the number c, is a rational zero of f. If c is a rational zero of f, then c is of the form p over q, where p is a factor of the last term and q is a factor of the leading coefficient. Okay? So in other words, the rational zeros of f have the form plus or minus factors of the last term divided by factors of the leading coefficient. So a couple things to note. First of all, this only works if the polynomial has integer coefficients. Second of all, this theorem only helps us find rational zeros. It does not help us find irrational zeros or non-real zeros. Okay? It only helps us find rational zeros. Another thing to note is the direction of the logic here. Right? We're saying if c is a zero, then it has the form p over q, not the other way around. Okay? Just because a number has the form p over q does not necessarily mean that it's a zero. Okay? It just means that it's in the running. Okay, it could be a zero. All right. So here's how we apply this theorem to sort of a general strategy for finding zeros of polynomial functions. Okay. So if I were confronted with just some random polynomial that I was trying to solve or factor or something like that, the very first thing I would try to do is I would try to use standard techniques to factor it, like the techniques that we reviewed back in section 2.2. Then, once I've done that, if there are any polynomials that are still too big for me to use the quadratic formula on or something, then I would try to factor them further by making a list of the possible rational zeros. The possible rational zeros are going to be of the form p over q, where p is a factor of the last term and q is a factor of the first term, right? So you make a list of the possible rational zeros, and then I would use synthetic division to test each of those possibilities until I find one that works. Okay? Now, personally, I like to start with the smallest positive integer on my list from step 2, and then I work my way up to larger and larger positive integers. The next thing that I'll test is the negative integers that are on my list. Okay? So I'll test the negative integers. I save any fractions as a last resort. Okay. Now, when I'm testing the positive integers, if you end up with a row of all positives in your synthetic division, okay, if that last row in your synthetic division is all positive numbers, then that means you found an upper bound on the zeros, so there's no need to test anything larger than that. When you're testing the negative integers, if you end up with if that last row in your synthetic division is a row of numbers that alternate in sign, positive, negative, then you found a lower bound on the zeros, and so there's no need to test anything smaller. Okay? So I test the zeros on my list. When I find one, then I would use synthetic division to see what polynomial I have left over after I factor out the corresponding factor to the zero that I found in step 3. Okay? Now the polynomial you're left with after the synthetic division is called the depressed polynomial. Okay? So once you found one zero, you factor it out and rewrite it as that factor times some depressed polynomial. And then you can repeat steps 1 through 4. That was a typo, but you can repeat steps 1 through 4 on the depressed polynomial. Okay? And then you just keep doing this until you end up with a complete factorization, or until you get everything down to linear and quadratic terms, right? So that's the strategy. Now, a couple more things that I'll say, and then the rest of the time I'm just going to be working out example after example after example, okay? But a couple more things to say. Don't forget that if you end up with a quadratic, you're done, right? You can stop there because you can always find the zeros of a quadratic polynomial by using the quadratic formula, okay? The other thing to keep in mind is that a number could be a zero more than once. If a zero repeats twice, then it's said to have multiplicity 2. If it repeats 3 times, then it's said to have multiplicity 3, right? And so forth. So once you find a zero, you need to retest that same zero on the depressed polynomial to see if that particular zero has multiplicity greater than 1. Okay? This method will guarantee that we find all of the rational zeros of our polynomials. There could be irrational zeros, there could be non-real zeros, and this method does not help us to find those. Okay, but it does at least help us find all of the rational ones, which is nice. So I have 6 examples. Okay, let's do all 6 of these. Okay, so we're supposed to find the zeros. Let's do it. So here I have a degree 4 polynomial. I could try to factor it by grouping. That would mean grouping the first 2 terms together. I could take out an x squared. I would be left with 2x plus 5. If I group the second 2 terms together, I could take out a -1, but then I'd be left with 4x plus 3. So factoring by grouping is not going to work on this particular polynomial. So I move on and I start to apply the start to apply the rational zeros theorem. Okay, so the list of possible zeros. So I'm going to call this PRZ, right? Possible rational zeros are going to be of the form plus or minus factors of the last term. In this case, that would just be 1 and 3. Those are the only factors of 3. Divided by factors of the first term. In this case, 1 and 2. Those are the only possible factors of 2. Okay, so this is going to be plus or minus 1 divided by 1 is 1. 1 divided by 2 is 1/2. 3 divided by 1 is 3. 3 divided by 2 is 3/2. Right? Okay, so those are the possible rational zeros. Now I'm going to start to test these possibilities to see which of them, if any, are actual zeros of the polynomial. So I'm going to start with the smallest positive integer, in this case 1. I'm going to test 1, and I'm going to see if it's a 0 by performing synthetic division. If it is a 0, I'll get a remainder of 0. So let's see. Drop this down, multiply, add, multiply, add, multiply, add. Sure enough, that was a lucky guess. Okay, but yeah, I found a 0. 1 is a 0. 1 is a 0. That means that x minus 1 is a factor. So maybe I should say f of x is now x minus 1 times what we have left here, right? 2x squared plus 7x plus 3. So I don't need to do any more work with rational zeros because I've got a linear factor here and then a quadratic factor there. So worst case scenario, I can use quadratic formula to find the zeros corresponding to this quadratic factor. Okay. Best case scenario, I can factor it. I wonder if I can. It would have to be 2x and x, and then it would have to be, I think, 3 here, and a 1 there will give me a 7, right? So there you go. There's the factorization. So the zeros are 1, negative 1/2, and negative 3. Okay? Let's look at another one. So I can start off by trying to factor this using normal techniques. It's not going to work out well for me. 1, 2, 3, 4, 5. 5 terms. If you have an even number of terms, you can try to factor by grouping. But when you have an odd number of terms like this, it doesn't work out quite as well. So I'm going to apply the rational zeros theorem. Possible rational zeros. They're going to be plus or minus factors of 16 divided by factors of 6. This time I think we have a little bit more work to do. Right? Factors of 16 would be 1, 2 goes into 16, 3 doesn't, but 4 does, 5 doesn't, 6 doesn't, 7, 8 does, and then 16 itself does, right? So those are the factors of 16. Factors of 6 are going to be 1, 2, 3, and 6. Holy schmoly, we've got a bunch of these things. Let's see. So it's going to be plus or minus 1, 1/2, 1/3, 1/6. 2. 2 divided by 2 is 1 again. 2/3. 2/6, which is the same as 1/3. Okay. 4. 2. Already written. 4/3. 4/6, which is the same as 2/3. 8. 4. Already written. 8/3. 8/6, which is the same as 4/3, already written. And then 16, 8, already written. 16/3. 16 over 6. 16 over 6 is 8/3, which is already written. Okay, so there we go. Those are all the possibilities. Okay, so let's start testing these. Again, I'm going to skip over the fractions. I'm just going to work on the whole numbers. I'm going to start with the positive whole numbers. If I don't find any zeros among the whole numbers, then I'll start to worry about the fractions, okay? But I'm going to start with 1. Got 6, negative 13, negative 24, 56. Don't forget your missing term, and then negative 16. Right? We have a 0x. That should be between the 56x squared and the negative 16. Okay, let's see. Okay, I don't know what this is. It doesn't matter, right? It's not 0. So 1 doesn't work. Let's move on to the next positive integer, 2. There we go. 2 works. Okay, so 2 works. Now, I don't think I'm ready yet to rewrite this. So notice, if I were to rewrite this, at this point I've got that this equals x minus 2 times 6x to the 0, 1, 2, 3, 4, 6x to the 4th. Oh, of course, right? We started with 6x to the 5th, and we just factor out an x to the 1st, so it's got to be 6x to the 4th minus x cubed minus 26x squared plus 4x plus 8. Now this has 1, 2, 3, 4, 5 terms, so I'm not going to be able to factor it using normal techniques. So I'm still going to have to do the rational zeros theorem. So I might as well just keep doing that now. Now remember what I said before, that a 0 could be a 0 more than once. So I'm going to test this on the leftovers now. So I'm going to test the 2 again, and I'm just going to do that by writing the 2 down here again and just doing this one more time. At least one more time. Zero. Aha, sure enough. Right? So 2 is a 0 again. What am I going to be left with now? An x cubed. That's still too big. Let's see if 2 is another 0 again. Could be. I have a feeling it's not. 46 minus 4 is 42. 84. 80. So no. So 2 is not a 0 again. So it's not a 0 again. It is a 0 these 2 times. I'm going to put a check mark next to them so that I remember what I've tested so far. Okay, so but 2 is not a 0 again. Maybe we could try 4. Oh, actually we don't have to, right? Because notice what this did tell us. This last row was all positive numbers. And remember, that means that we found an upper bound on the zeros. So we know that there are no zeros greater than 2 for this polynomial. So I don't need to check 4 or 8 or 16. I don't need to check any of the rest of them. So maybe I'll start testing some negative numbers. Maybe I'll test -1 and see what I get. -1. I'm gonna do -1 on this polynomial right here. This is what I've whittled it down to so far. So let's test it on this one. -6, -6, 5, -5, -9, 9, and 5. Okay, so -1 is not a 0. Maybe -2 is. -6, -12, -1, 2, -2, 4. There we go. So -2 is a 0. All right, so what do we know? We know that f of x is x minus 2 times x minus 2, right? We had those 2 zeros, and then an x plus 2 here, and then a 6x squared plus x minus 2 left over. Okay, so I'm going to finish this. Let me just pause this real quick. Okay, I'm back. Okay, sorry, my daughter's in here. She wanted to come in and see what I was doing. Okay, so this is what we have so far. Now, if I can factor this any further, then I will. If not, I can always use quadratic formula on it. Let me at least try to factor it, though. For 6x squared. Well, we could have 6x and x, or we could have 3x and 2x. 6x and x. I think it's going to have to be a 3x and a 2x. Could be wrong. 2 can't go there. 2. Well, so then that would force this to be 1. We'd have 3 plus 4. Oh, that'll do it. That'll do it, of course. All right, so we should have a positive 4 and a negative 3 to get us a positive 1 there. So there we go. There's the complete factorization. So my zeros are 2, right, multiplicity 2, negative 2, negative 2/3, and 1/2. So there they are. Notice that all of the zeros of this particular polynomial were in fact rational numbers, and notice that they're all on the list of possible rational zeros, right? They're all on the list. 1/2 is on the list, right? Negative 2/3 is on the list. Negative 2 and positive 2 are all on the list. But there you go. That's how you find the zeros. Okay. Anytime you have a zero of multiplicity greater than 1, I want you to do this. I want you to tell me, this is a 0, and then tell me what its multiplicity is. If the multiplicity is 1, then you don't have to write multiplicity 1. But if it's more than 1, tell me what the multiplicity of that 0 is. Okay. So that's that. That was, wow, that one was a doozy. Let's look at another one. Okay. So we want to do x cubed plus 29/4 x squared plus 6x minus 9. Now right off the bat, this is fishy because rational zeros theorem is only going to work when you have integer coefficients, and this is not an integer. So here's how we can handle something like this. First of all, when we find the zeros, that's really equivalent to solving the equation f of x equals 0, right? So I'm just going to take this polynomial and set it equal to 0. And now I'm going to clear that fraction by multiplying through by 4. Then I get 4x cubed plus 29x squared plus 24x minus 36 equals 0. Now this polynomial I can apply the rational zeros theorem to, right? So I can say, well, first of all, maybe I should try to factor it using normal methods. Here I could take out an x squared and be left with 4x plus 29. Here, no matter what I factor out, I'm not going to be left with the 4x plus 29. So no, I can't factor by grouping. But I can make a list of the possible rational zeros. They're going to be factors of 36 over factors of 4. Oh man, so that's going to be 1, 2, 3, 4, not 5, 6, 7, 8, 9, 12, 18, and 36. Oh, this is going to be a pain. Okay, and factors of 4, 1, 2, and 4. So my possible rational zeros are plus or minus 1, 1/2, 1/4, 2, 1, 1/2, 3, 3/2, 3/4, 4, 2 and 1, 6, 3 and 3/2, 9, 9/2, 9/4, 12, I'm going to run out of room, 12, and some more. Okay, I'm just going to say ... because I've got plenty of things to try out, so let me just start trying some stuff. Again, I'm going to do this on this polynomial here, not the original. Okay, so let's try out 1. Let's see if 1 is a 0. 29, 24, negative 36. Okay, so we've got 4, 4, 33, 33, 59, 59, and then I don't know what this is, but it's a positive number, it's not 0. And look at this, right? I'm already, even just using 1, I get a row of all positives. What that tells me is that I don't have any zeros bigger than 1. So I've already reached an upper bound. So I'm not going to test anything bigger than 1. 1/2, 1/4, they could still be zeros. 3/4 might be a 0, but definitely 2, 3, 4, 3/2, 9, 9/2. None of those numbers are going to be zeros. Okay, I already know that because I got this row of all positives. So what I'm going to do then instead is start testing the negative zeros, or negative possibilities. So I'm going to test negative 1. -4, -4, 25, -25, -1, 1, and -35. Okay, so -1 doesn't work. Maybe -2. So 4, -8, 21, -42. 24 minus 42, -18. Oh, there we go. 36 and 0. We got a winner. There it is. And what I'm left with now is a quadratic, so I can be finished. So I know that x plus 2 is a factor. So I've got x plus 2 times 4x squared plus 21x minus 18 equals 0. Should I even bother trying to factor this? Well, maybe it's not so bad. If I use 18 and 1, 18, 22, maybe not. I don't know. That could be factorable. Maybe it's not. I'm not going to scratch my head over this forever. I'm just going to use quadratic formula on this. So as far as this one's concerned, I know x is -2. As far as this one's concerned, I'm going to say x is -b plus or minus square root of b squared minus 4 times a, which is 4, times c, which is -18. So this is really plus 228 divided by 2 times 4, which is really 8, right? Divided by 8. I wonder, 441 plus 228 is 669. Is that a perfect square? It is not a perfect square. So yeah, we wouldn't have been able to factor that. So that's fine. In fact, square root of 669, maybe let me check my work real quick. So I've got 21 squared minus 4 times -18 is 729, not 669. Sorry. Where did I go wrong? Four times 4 times 18. What in the world? I'm having some trouble with arithmetic. B squared. 21 squared is 441. 4 times 4 times 18 is 228. 441 plus 228 is 669. And yet, when I put in 21 squared minus 4 times -18, I get 729. What in the world? Okay, 288. Oh my goodness. I'm sorry. Okay, it was because I was putting 228 instead of 288. It's 288. This is 288. There you go. Okay, well this would be factorable then. This is negative 21 plus or minus square root 729 over 8. Oh my goodness. You're probably sitting there watching this saying, this is our teacher? Sorry, you're stuck with me. Okay, negative 21 plus 27 divided by 8 is 3/4. So we get x equals 3/4, or if I subtract, it would be negative 21 minus 27 divided by 8 is negative 6. Okay, so I'm running out of room here, but I'm going to put my answer up here. So the zeros are negative 2, 3/4, and negative 6. Sure enough, notice that none of my positive zeros were bigger than 1, right? The biggest positive zero I got was 3/4, right? That was an upper bound. The other two zeros were, of course, negative numbers, all right? So that's kind of interesting, but there you go. All right, so there's that one. Wow, wow, wow. Okay. Very good. So another thing that I want to point out is that it was totally necessary to do this step that we did at the very beginning. Remember that the rational zeros theorem does not apply if your coefficients are not integers. And you can see that. If I had tried to use the rational zeros theorem on this, I would have said it would have been factors of 9 over factors of 1. So I would have gotten 9, 3, and 1. Those would have been the only possibilities, and none of those are zeros. So it wouldn't have gotten me anywhere, right? So they have to be integers. That's why this first step was absolutely necessary. Let's do another one. Okay? Part D. Now, Part D presents a different challenge, right? Because our constant term here is 0. And if you remember in the statement of the rational zeros theorem, we said that the first term and the last term were not allowed to be 0. So you can't apply the zero product or the rational zeros theorem to this polynomial. So what do we do? Well, it's an easy fix. Because the last term is not 0, that means that all the other terms have an x in them, which means you can factor out an x. If I factor out an x, I'm left with 3x cubed plus 4x squared plus 23x, minus 23x plus 6. And now this polynomial, it does have, its last term is non-zero, okay? Its constant term is non-zero. So we can apply rational zeros theorem to this polynomial. Of course, before we do that, we should see if we can factor it by normal means, and I don't think we can. So we're going to have to make a list of the possible rational zeros. They're going to be factors of 6 over factors of 3. Oh, thank goodness. This is a little easier, right? Factors of 6. 1, 2, 3, and 6 over factors of 3, 1, and 3. That's going to be plus or minus 1, 1/3, 2, 2/3, 3, 3/3, 6, and 6/3, which is 2. Okay, so there are the possible rational zeros. Let's test them. Starting with 1, got 3, 4, negative 23, and 6. This isn't going to work, is it? Negative, what is this? Negative 16. Okay, so that doesn't work. I can try 2. So 3, 6, 10, 20, negative 3, negative 6. There we go. Okay, so that tells us that f of x is x times x minus 2 times 3x squared plus 10x minus 3. I wonder if we can factor that. That's x times x minus 2 times, we'll try 3x and x. We'll try a 3 there so we can get a 9 and a 1 there so that hopefully it makes a 10. Probably not though, now that I'm thinking about it. Oh, this isn't going to be factorable, is it? So b squared is 100 minus 4 times a times c. So it's really 12 times 3, 36. 136 is not a perfect square, right? So it's not going to factor. So we have to use quadratic formula on this one. So on the one hand, I'm going to say, from this term I get x equals 0. That's 1, 0. From this one I get x equals 2. That's another 0. And from this one I'm going to get x equals negative b plus or minus square root of b squared minus 4 times a would be 12 times c. 12 times 3 is 36. Negative 36. So minus a negative 36, right? Plus 36. Divided by 2 times a is 6. I better use my calculator again to check my work. 10 squared. I would have gotten in trouble last time. 10 squared minus 4 times 3 times negative 3 is 136. Okay, thank goodness. Square root 136. That reduces to 2 root 34. So it's negative 10 plus or minus 2 root 34 over 6. We can reduce by 2. That's going to be negative 5 plus or minus root 34 over 3. Okay, so there we go. There are the zeros. X equals 0 is a 0. X equals 2 is a 0. X equals negative 5 plus root 34 over 3 is a 0. And then x equals negative 5 minus root 34 over 3 is a 0. Okay, so there we go. All right. Mags. Okay. Last page. 2 more problems. Part E. Oh, wow. Deceptively easy. Actually, it's difficult, I guess, this problem. So let's just try to solve it. So first of all, we can't factor this by any normal means. You could think of this like a sum of squares. Sums of squares are not factorable, right? Or at least they're not factorable over the real numbers. Which isn't necessarily a huge issue, but even if we factored this, we can maybe factor it like it would have to be x squared plus I times x squared minus I. And if you're confused about where I'm coming up with that, don't worry about it. We'll talk about it in the future. But this would be a good factorization for x to the 4th plus 1. But now how do we solve for x? It's like you end up having to take the square root of I, and we don't really know how to do that. So that approach isn't really going to work yet. We'll talk about that in a little bit more detail. But for now, we're stuck using that approach. Maybe we can try to apply the rational zeros theorem. Right? If we make a list of the possible rational zeros, it's going to be numbers of the form plus or minus factors of 1 over, well, factors of 1. Right? So plus or minus 1. Those are the only possible rational zeros. And guess what? Neither of them works. 1 is not a 0. 1 to the 4th plus 1 is 2. And negative 1 is not a 0. Negative 1 to the 4th plus 1 is also 2. So there are no rational zeros. We're stuck. We're stuck. It's not that this thing is unsolvable. It's just that the zeros are not rational. So the rational zeros theorem doesn't help us find the zeros of this particular polynomial. We will come back to this. By the end of the chapter, you'll be able to solve this. But for now, we're going to have to come back to it. Well, let's do one more. Oh, what do we have here? X to the 7th minus 3, blah, blah, blah. Well, we've got an even number of terms, 1, 2, 3, 4, 5, 6. We could try factoring by grouping. Oh yeah, factoring by grouping will work here. This is one of those rare circumstances. If I group these first 3 terms, I can take out an x to the 5th, and I'm left with x squared minus 3x plus 2. And then if I factor the second group, I can take out a negative 1, and I'm left with x squared minus 3x plus 2. And now notice these things match. So I can take that out, and I get x squared minus 3x plus 2 times x to the 5th minus 1. Good. Can I factor this any further? Well, yes. This one, I think I can do x minus 2x minus 1. As for x to the 5th minus 1, if I do the possible rational zeros thing, I'm going to get plus or minus 1, just like I did up here, right? Right? But what makes this different is that I think positive 1 is a 0, right? 1 to the 5th power is 1, 1 minus 1 is 0. So positive 1 is another 0. Let's see what I get when I do synthetic division. So I have an x to the 5th, 0x to the 4th, 0x cubed, 0x squared, 0x minus 1. Get 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and 0. Sure enough. So what does this mean? Well, it means that, well, I could try 1 again. Let's try 1 again. Let's see. You get 1, 1, 2, 2, 3, 3, 4, 4, 5. Oh, and then I'm done, right? Well, that clearly didn't work. So 1's not a 0 again. It's only a 0 once. Negative 1 is not a 0 at all. Okay? You can see that clearly from here. Negative 1 to the 5th is negative 1. Negative 1 minus 1 is negative 2, not 0. And since those are the only 2 possible rational zeros, I'm kind of stuck at this point, right? Here's how far I can get. I can get to x minus 2 times x minus 1 times another x minus 1, right? This x minus 1 came from here. But I have another x minus 1 that comes from there, right? X minus 1. And then what am I left with? I'm left with x to the 4th plus x cubed plus x squared plus x plus 1. And now I'm stuck on this one. I can't go any further with it. I can't find any more zeros. So I'm kind of stumped. Right? Stumped again. Okay. So these last two problems are really meant to be teasers, right? They're meant to show you that, well, we haven't quite finished talking about all of the techniques for finding zeros yet, right? There's more to discover. So we will do that in future sections. But the rational zeros theorem is still a pretty good tool for finding lots of zeros. It helps us find all of the rational ones anyway. But that's all I've got for 4.2. We'll see you in the next. We'll see you in the next section.